Start. So welcome to the sixth session of the SwissNLP Crash Course. In this Crash Course series, we're learning about natural language processing and the different applications of AI for language. And today we have a nice talk by two speakers from Karakun, Dr. Holger Keibel and Olmo Barberis. So
Hi.
It's really nice to have them here today. So before we start with the talk, I want to advertise the SwissNLP Days. The Crash Course series is leading up to 3 days in May, so from the 13th to 15th of May, where there will be a scientific conference, but also an industry exhibition on the 13th of May. So if you are interested in the topic of today's talk, then likely you will also be interested in the exhibition and the SwissText conference. Registration has started yesterday, so now is the right time to check it out and register. So with that, I would like to lead over to Holger and Olmo, and I'm really looking forward to that talk.
Thanks a lot. Thanks. So maybe I will start. Hi, everyone. I'm Olmo Barberis. Welcome to our crash course. And today with my colleague Holger, we'll talk about how to leverage AI for automated document processing. But before starting, a few words on our company. Next slide, Holger. Yeah. We are based in Basel with Karakun. We are a general software company, mostly focused on building sustainable custom software solution in different industries, especially for use case where there is no suitable standard products actually existing in the market. And to facilitate this, we provide several software platforms, and in particular of interesting for today, it's our Keibel platform for solutions in the area of search and natural language processing. So that's about us and about today's agenda. We'll focus mainly on 3 topics today. The first one, an intro by Holger on what is automated document processing. And then we will present two use cases, text classification and information extraction, and possible approaches for those 2 use cases. Unfortunately, due to the time constraint we won't have time to show other use cases, like, for example, text summarization or text translation. And then in the end, we will sum it up with the conclusions, what we talk about. So let's start. And Holger, the stage is yours.
Thanks, Olmo. So yeah, first item on the agenda, what is automated document processing? First of all, what this term by itself is ambiguous, and what we mean by it is really the processing of the contents of documents, not so much the technical processing, handling documents, moving them around and stuff like that at the file system level, for instance. But we will say a little bit about that also in one of the next slides. So in a nutshell, here in this blue box, we describe automated document processing as the task to analyze the documents, or a document by its content. And the document content usually is unstructured data, running texts, optimized for humans. And the task now is to analyze this document content and derive from it some structured or at least some condensed data that's relevant for a given purpose. And this structured or condensed data is then usually optimized for machines to process. And this is also the main purpose why we do that, right? We want to do document processing to kind of assess the information that's in these documents and to allow machines to also interact the contents of these documents and process them further, and they require these structured or condensed data. And therefore, the results of document processing can then, and that's the yellow box, can then be fed into other systems, for instance, for further processing, for instance, to a search system, to an ERP system of a company, to a business intelligence tool, and so forth. Or it can also be used, the results can be used to directly trigger some actions right after the document processing step. For instance, actions in the form of email triage when you have a central email inbox of maybe an insurance company and emails keep coming in, then there's not just one person or one group of people answering these emails, but they're first distributed to the right department or even to the right team. And therefore, the email is automatically analyzed for its content. And then depending on that content, it will be sent to the right team inbox or department inbox. A third application is that the results basically constitute the final result on their own right. For instance, the results of document processing can simply be added to the document itself in the form of document metadata. You've probably all seen in PDFs or even in Word documents, you can add metadata to the document. For instance, we could analyze the document type. We will say more about that later, and add that to the metadata, and that's a form of enrichment. The benefits of doing document processing is first to reduce the manual effort because it's automated, to reduce the degree of inconsistencies. If there's multiple people doing these tasks manually, you can expect the results to differ even on the same documents. And the goal is also to reduce the degree or the percentage of errors. But this is, of course, the most challenging part here. The automated document processing mechanisms are also not error-free. The goal is also to increase the processing speed and the efficiency. And in particular, it helps to find documents and information within a company, for instance. So this brings us to information retrieval. But overall, as I said, the goal is to feed the results to other systems very often, like here. And this basically gives rise to automation pipelines. But the first step in these automation pipelines is really to extract the data and turn them into structured data. So now, as Olmo already said earlier, there's basically 4, possibly more, but these are at the highest level that we can distinguish 4 different use cases of document processing. The most prominent one is to assign categories to text or to documents where you take the document or the text really as a global thing, and you want to assign to it one or multiple categories, and these categories come out of a predefined set of categories. For instance, you can go for the semantic document type, which could be contract, invoice, a CV, a manual, a bank statement, and so forth. Or you could have a very simple category system, a binary one with just 2 categories, spam versus no spam in email spam detection. Or you could analyze the whole content of a text and decide by means of sentiment analysis whether the overall, the tonality of the statements in this document is rather positive or negative. And of course, there could be more values than just positive and negative. It could be neutral also, but in the most simple form, sentiment analysis goes by just 2 categories. The second high-level use case is information extraction. Here, you again take the entire document, but you don't want to treat it as a whole, but you really look at the individual parts in it, the individual pieces of information in the content, and try to find those pieces of information that are relevant for a given task. And these pieces of information usually are either named entities like persons, locations, organizations, and so forth. This would then be the classical named entity recognition, short NER. Or you could go for special keywords, which can be general language terms or expert terms in a certain domain. Here in the example, we have fee, population, the term software could be of interest, and so forth. Or you could go for values like dates, quantities, monetary amounts, bank account numbers, measurement values, and so forth. So these are normally single data points, these things that are listed here, but you can also be a little bit more ambitious and try to extract or derive from the content facts in the form of knowledge graph triples, which are triples of subject, predicate, and object. For instance, you could be interested in knowing from the document that a person called Peter owns an object called house, something like this. And this could also be part of information extraction and then maybe added to an existing knowledge graph. The third high-level use case is text summarization. There the task is really, again, to take the text as a whole and to summarize the core messages in this text and kind of create a shorter text that really summarizes these core messages. But it doesn't always have to be full text the result doesn't have to be a full text with full sentences. It could also be just a couple of words. And one special case would be the task of topic identification, where you basically describe the main topic of the overall text with a short label. And an example could be this annual energy statement 2018. Here, very often you can just go and not really write a new text or new words, but you can really go and find the most prominent terms in the document to describe the core topic of this document. And then there's, of course, text translation. I'm sure you've all interacted with either Google Translate or DeepL, and there's other machine learning translation systems out there. Also LLMs, large language models, can translate fairly well. And basically here the task is to translate an entire text from one language to another. And if it's just raw text, then that's really what this is about. But if you have like a web page, for instance, you very often want to translate the contents while retaining the document layout and formatting, so that you still get a web page that you can look at in the browser and looks exactly the same, just the text is translated. Google Translate does that when you have the browser plugin, for instance. So these are the 4 high-level use cases. But as Olmo already said in the beginning, we are only going to look at these 2, text classification and information extraction. And before we jump into them, basically 2 things up front so we can focus on the core topic. Of course, normally you don't get just text and then can analyze it the way I just described, but you normally get documents or files that contain text. And so you normally have to do some pre-processing to get to the content that you actually want to analyze with the document or text processing. And if you have, for instance, an incoming file that's a text file or an Office document, it's fairly easy to derive the raw text from it. For PDFs, the same applies, of course, for HTML or just web documents. It's also fairly easy to derive the raw text from it. It's a lot more complicated if you have an image file or a scanned document, which very often is not really an image file formally. It very often comes as a PDF, but inside that PDF, you first get only image pages really, and you don't have any text in that. To get the text, to extract the text out of the images, you have to apply something called image to text, or OCR, for optical character recognition. And that will then produce a digital text version of the content of that image or all the images in that file. The same applies to audio files. Here you don't have readily available the raw text. You have to apply something called speech to text. This is basically transcribing the audio content, the spoken audio content, to digital text. So you have raw text as a result from the 2, and something similar also for video content. Now, very often, in the end, you only want to analyze the raw text, so this is all you need to worry about. But sometimes you need to know a little bit more. For instance, when exactly in an audio file or video did the speaker say a certain thing? So you record additional information, like the time of utterances or of words. With OCR, you want to sometimes know something about the layout. Where on a page did a word occur? So you actually might be interested in X and Y coordinates of these words. And therefore, I wrote here that the result of these steps can be raw text plus additional information. We get back to that in a moment. Then sometimes you have to clean the resulting texts and also correct the ordering of words in it. This very often applies especially to PDF documents. Imagine you have a PDF page with 2 columns and then some text boxes. If you just extract the raw text from it, you cannot really rely on the text being ordered in the way in which you would read it. You might have the scenario where you have 2 lines from 2 different columns that appear on the same height, and you get basically the content of both these lines right after each other, so you cannot really read the thing anymore in the extracted raw text. So you have to correct this order somehow, and you probably have to do it. It's best to do that very early on. Then afterwards, there's some initial NLP pipeline applied. It's not always all these steps here, but you can apply some of these lower level NLP tasks depending on what you want to do with the raw text afterwards. And then we come to the part that we're interested in, the text processing, with these 4 types of use case that we described. And that, here again, is the text processing that gives you the results, which can be when we have classification, we get the assigned categories, the extraction, we get extracted information and so forth. And these results sometimes then have also be subjected to some form of post-processing, which is essentially about validating or even fixing values if they deviate from what you expected to get or what you support as values. This also often involves some normalization. For instance, number formats, you might want to normalize the thousands separator in numbers. For currency amounts, you want to normalize the way you write the currency. You want to remove some space characters or normalize hyphens and so forth. And there's more that can happen here. And then in the end, you have the results that you will basically export to whatever subsequent system gets these results as input. And with that out of the way, we can now focus on the actual document or text processing step. And with that, I hand over back to Olmo.
Thanks, Holger. So now we'll look at the first use case, which is text classification. We'll show you 4 possible approaches and briefly explain them and highlight the pros and cons of each approach. So let's start with the first one, which is a rule-based approach. And what we mean by rule-based approach? Usually, in this case, for each document, you define a set of rules for each possible category. For example, a set of rules for detecting contracts, a set of rules for detecting invoices. Then those rules are matched against the whole document content, and you have a certain amount of matches inside the document. And then the most simple solution, like we have in the graphics in the upper right corner, we have 4 matches orange, which means that this document is a contract. And in the one below, we have 4 matches blue, which means that this document is an invoice. And usually in that area, rule is regular expressions, which is a way to express a sequence of characters and words that you expect in the document. Like we have the example here, total amount due. This regular expression can matches the words total amount or amount due in the document. And this can be an example of a rule for detecting invoices. Extracting the most used rules, maybe it's just the most simple solution. Then there is more other elegant solution, like for example, assigning a weight to each rule, because maybe total amount is more important than other set of words inside an invoice. And if you assign a weight to each rule, then you can compute a total score for the document for each category and then decide which category assigned to the document. What are the pros and cons of this approach? There is no need to do any training, so there is no model, there is no specific hardware where we have to run this approach. It's can be run even low resources environment. You don't depend on a training data set or your starting data set. You don't need a huge amount of documents to start working on that. But there is a downside on that as soon as your data set grows, as soon as you have more and more documents, you have to implement more rules. And maintaining and scale those rules, it's always a little tricky. It requires a lot of time. You have to invest time on adapting the rules. Adding new rules should not break the result of the previous set of rules. So it's time consuming and it's difficult. You also need deep knowledge of your document set. You really need to know all your documents, how they're structured, what is the content of your document. That's the downside, but the upside of that is that it's highly customizable. You can really handle all the corner cases, maybe a subset of specific documents have some really specific words, and you can just add some rule for those subset, and then that's handled. So there is some pros and cons, but it's a good starting point if you have a document set where you can really differentiate easily with some specific words, some specific keywords inside the document. That's a good approach to start. But for maybe more complex case, we can look at the next approach, where if you can go to the next slide, Olga. Oh, yeah, where you can use statistical machine learning algorithms. Here we are in the field of supervised learning, means that we use labeled data to train algorithms into classifying data or predicting some desired outcome. Like in our case, is predicting the class of the document, like contract and invoice. And here, for a deeper overview and explanation, what are those machine learning algorithms, you can go back to the first talk of this crash course, what is natural language processing, where you have an overview of most of those algorithms. And as there are many of them, like for example, linear regression, logistical regression, support vector machine, which is shown in the graphic in the upper right corner. And what does this approach imply? It implies that you require to manually define some features in your document that are measurable. A feature can be how frequent a word is, if there is some specific words or not, or the structure of the document, how long it is. If it's 120 pages, probably it's not an invoice, or you're going bankrupt. And combining these features, you extract them, they're measurable, you have a value for each feature, you can generate a vector, and then those vectors are provided to the algorithms, you train it, and then you can use the trained model to do the actual classification on your real data sets. This approach has some pros. You can retrain your model as soon as your data set grows and improves your results. So it's really future-proof because it grows with you. There is no need to discover patterns or define rules like in the previous example, because this is done automatically by the algorithms. But you need to define the feature. So there is some requirements for the feature engineering. This is a downside of that. And you need to know the documents to choose the right feature, the meaningful one. And you need to know which are more meaningful, how features are related one to another. Another advantage is that it's scalable, can easily handle large data set and also complex language variations. That's not an issue. But you depend on a large amount of labeled training data to start with a model that can really extract some valuable info from the features and perform a meaningful classification. And also it's sensitive to data quality, because biased data or noisy data really hurt your model. And about biased data, you can also go back to talk number 4, if I recall correctly, to us bias in NLP, if you want more information on that. And this is for statistical machine learning algorithms. The next approach here, again, we do a step forward from machine learning to deep learning. Deep learning is still machine learning, but uses a more complex and deep structure, where you have neural networks with a lot of layers and use them to make predictions. The most famous model here is BERT, which has been recently updated with a new version, Modern BERT. And those models are, of course, more complex, but it also means that they are more resource hungry compared to the previous approach. And in the talk number 2 in the crash course, talk number 2, you can have a deeper look into how small language model and large language model are pre-trained and fine-tuned. And one thing that you also need to keep in mind is that between the statistical approach and this deep learning approach with the small language model, there is also other approaches in the middle, like long short-term memory, which was the state of the art for quite some time. But yeah, due to time constraints, I will not cover that today. We'll focus on small language model. But it's worth knowing that there are other approaches. And how does that work? A model is basically transformed again into a vector, but you don't need to do feature extraction automatically. There is a tokenizer that handles transforming words or documents into a vector. Then this it prepares the input for the model. Then the model is trained on that. And usually a model like Bern is provided pre-trained. It means that it's trained on a large data set and it gains some knowledge of the language that way. And then you can fine tune it with a smaller data set, just a few hundreds documents for each category. You can fine tune your model for a specific task in a specific domain. Like, for example, classifying invoices versus contracts versus bank statement. And yeah, the pros and cons of this approach is small language model really capture the context, the meaning in the context, the meaning of a word related to other words, even distant one in the same document. So it's more precise because it can really extract the meaning of the document. As I said before, you don't need any feature extraction, manual feature extraction. That's up to the model to do it, to the tokenizer and the model. And it's easy to fine tune using small data set on a specific target. You don't need thousands of documents like for statistical machine learning algorithms. The downside, of course, is that those models are big, so you need dedicated hardware, especially for training, you need GPUs, while for inference, usually for running them, you can leave it with CPU machines, but still you need a lot of memory, a lot of powerful hardware. And even if they're that powerful, you still need quality labeled data to do the fine tuning. Because without data, even a small data set, but without quality, you don't get anything meaningful from that. That is if you have even a small data set, but it might happen that you don't have any training set as a starting point. So another approach in that case could be what we see in the next slide, is to use what it's the hype now, so large language models with some custom prompts to do text classifications. And large language models, just a few words as background, they share the same structure as small language models, but they are trained on much larger data set, multilingual data set often. To train them, you really need large-scale resources, data centers for both training and also for inference. You need some powerful machines. But those language models, they have a broader knowledge. They know about multiple topics. And you can use the same model to perform a lot of different tasks. As we have seen in all the previous talks, you can use for really a wide amount of topics. And you can use that for classification. Especially, it might be useful to do zero-shot classification or few-shot classification. Zero-shot classification or few-shot, it means that you make the model predict a class and that it wasn't seen during the training. It's not something that the model was trained for that. The model is more generic, but still it has the knowledge to perform classification. Maybe you have to provide some examples from your document in the context, in the prompt. And if you provide some example, is the few-shot classification. If you don't provide an example and just say to the model, okay, that's the document, Those are the possible classes. Which class it is this model? That's zero-shot classification. And you can achieve some good performance by tweaking the prompts, using some custom prompts. You can really leverage the power of those large language models and get some good results. The advantages here is that it's really easy to set up. You can use a third-party provider, OpenAI, Mistral, or whatever, and it's really easy to set it up. You don't need any dedicated hardware in your environment. You don't need any training data set. You can start without any documents, just perform, as I said, zero few-shot classification on that. And another advantage is that those models are flexible. You can provide them both text and images and can work also with that, not just with text. The downside here is, of course, it's really heavy, really big model, so it's computationally heavy, can easily be expensive, especially if you try to classify big documents. Then the context is big, you pay per token, and usually that's easy to make cost explode. It might be overkill to use such a powerful tool just for a simple task like text classification. It's not the usual use case, so it might be a little overkill. And it might be difficult to provide a valid prompt, a meaningful prompt. There is some framework that can help you to generate prompt that is valid, but it's not always so easy. So those are the downsides of using LLMs. Those are 4 possible approaches for text classification, but it might happen that you don't need text classification, but you need document classification. You might have some type of documents where maybe the font is important or the logo, some specific documents, maybe ID cards or that way, or those kind of documents. And you don't need the text for classifying those kind of documents, but you can rely on image. And in this case, so text is not enough to classify. You use the image, you can train a neural network. Usually in those situations, you can use a convolutional neural network, and you train a model to do image classification. And it works really well, often, depending on if you have a specific use case for that. You cannot provide just image of a book because of pages of a books, because that's document where you have a lot of running text. But for ID cards and passports, credit cards, or other specific documents, that works really well. So you have a high accuracy for that. The downside is, as usual, you need a training data set with a lot of labeled images, and it's always time consuming and difficult to build your data set. It's also more resource intensive compared to rule-based approach or more simpler approach. And often those neural networks are black boxes. So you see the image in input, you get the output of the model, but it's difficult, especially if you don't have great result, it's difficult to understand why it's not working. You don't have an immediate and visual comprehension of what is going wrong. So sometimes it's difficult to work when you have issues. And yeah, that's the last approach. Maybe to sum it up, these four or five approaches, some takeaway from me, it's that AI is not just LLMs and generative AI is not always the best answer. There is a lot of approaches that are maybe older approaches, but they are still valid, they're still explored and improving from time to time. So do not use generative AI for everything today. It's not always the best approach. And of course, it's difficult to choose which approach to follow. There is a lot of factors that heavily influence your choice, especially cost factors, so performance, quality expected, and so which approach to follow really depends on a lot of factors. But there is no need to follow just one approach. One approach does not exclude another one. For example, if you don't have a training data set, you can start with zero-shot classification using an LLM, and this can help you create a data set. Or, well, I'm not ashamed to say that we have we have followed some rule-based approach in our solution. And I'm not ashamed to say that I had the help of my good friend ChatGPT to create some regular expressions. So you can really mix the approach together and get the best out of all. Yeah, I think that's all. So let's move to the next topic. I hand it over to Holger for information extraction.
Thanks, Olmo. Yeah, so information extraction, this part is structured a little different from what Olmo just did for text classification, mostly because the possible approaches or the for information extraction draw from the same set of fundamental methodologies. So I don't have to repeat the things Olmo already said. So I will structure this part rather by looking at the different types of challenge that information extraction might encounter and recommend suitable approaches for each of these challenges. And this also makes sense for a second reason, because the task of information extraction can vary quite considerably across different documents, different extraction needs, different types of information that need to be extracted. So the complexity is really of the task itself is a bigger issue than for the text classification. And that being said, the first and most the first thing that really comes to mind when you think of information extraction is really to extract relevant information from running text. That's one form of sequential textual data. It's kind of the prototype of that. You just have full sentences, in this case, the beginning of a kind of a letter. And here I already highlighted the pieces of information that might be of interest for an information extraction tool. There's a person name, a named entity, there's a monetary amount, there's a date, there's an organization name, company name, but there might also be other things of interest here. I just highlighted these. And for this type of task, to extract information from running text in the form of named entities or keywords or values, usually the raw text itself is enough to do the task. So this means you don't need layout information about where exactly on the page a specific word occurs. And there's basically all methods that Olmo mentioned in his part before that are suitable here as well. For instance, with a rule-based approach, here you can start with regular expressions. I gave you an example here without going into the technical details, but basically this tries to find monetary amounts, but only for Swiss francs. But Swiss francs can be spelled in two different ways here, and then with this we hope to find this as a match. There can be an apostrophe here, but it doesn't have to be. There can be some 2 digits after the francs amount. And so this will basically detect instances like this. And the same would apply also for dates, only slightly more complicated because there's more variation for dates. And but it's already a little more challenging to extract person names and company names. You cannot, unless you know all the names that are of interest. You know, if it's if it's a finite list of person names that you're interested in, then you can basically set up this vocabulary and in a keyword-based way, or even with regular expressions, if there's some variation with the possessive, you know, like os Brunners, you know, if there's a plural S or a genitive S here, then you can work with a keyword list and some basic regular expressions to find that. But that's normally not what you would do for names, for named entities. You would rather go for these other approaches here. So statistical machine learning and also the long short-term memory systems, those neural networks, here you would basically go and turn this extraction task into a classification task. And just in a nutshell, this works like this. You basically train the system with either engineered features for statistical machine learning or just from scratch with the neural network here without feature engineering, and give it the task to decide for every single word token in turn whether or not it's part of a named entity or of a value that's of interest. And then you give it, of course, training data where the decision was already made. And then in the end, you basically can color code, if you will, color code the words if they are part of a named entity or not. And then in the second run, you have to decide if Urs Brunner, if these two words belong together to the same entity or if it's two different entities. There's also approaches, especially with LSTMs, where you can do that right away and you assign this the word Urs, the tag, this is the beginning of a named entity, and then Brunner, the tag, this is the ending of a named entity. And if there's 3 words, then you have also a tag saying this is kind of in the middle of a named entity, and then it's easy to collect the things that belong together later on. So that's kind of the clever trick to solve extraction, information extraction by means of classification, which is just what most of these systems really are trained to do. Or was set up to do. It's different for small language models and large language models. These, because the way they work, they can actually do the task more directly. With small language models, you probably have to do some additional training, some fine tuning to tune it to the actual task. But with LLMs, you can really work with one or few shot approach and just ask with the right prompt, ask the model, here's my text, give me all the named entities or all the dates or all the monetary amounts in this text. So that's the most simple scenario. If we go one step further, we still have sequential textual data, but we have not running text, not full sentences. Rather, we have kind of a label here, order date, and then a value that we are interested in that we want to extract. So basically label value pairs, but here they are aligned horizontally. So they're on the same row. And here too, layout information is rarely needed. And again, you can start with a rule-based approach by means of a regular expression here, looking for the label, order date, but not extracting this. So this is kind of what this question mark and these other 2 characters here do. Say that I want to find this, but I don't want to extract it. I'm interested in this stuff here. And that's basically everything that follows until the end of the line. And so we extract the green stuff here with this pattern. The same would also work here, even though there's some stuff in between, or except for the colon that's missing here. So the pattern would not fully work here, but almost. But the space here is not a problem for the rule-based approach. And even here, if you have the label here, and then there's some stuff between the label and the thing you want to extract the value, it's still easy to come up with a suitable regular expression that would still find this based on this label. But you can do the same thing again for statistical with statistical machine learning and also with these other neural approaches. So this is something that's fairly easy to do, but very often actually rule-based approaches are just fine for this type of problem. The third case is already more tricky. It's really more challenging. That's again label value pairs. You have a date and then the date value. You have the label reference and then the reference value and so forth. But in this case, they are aligned vertically. And so this is not really sequential data anymore. It's if you read this line by line and then from each line from the left to the right, you have the label date, and then you have the label reference before on the next line, the value for date appears, and then the value for reference. And you can easily imagine if there could be more labels or more stuff in between. So that's something that's harder to do directly with one single regular expression with a very simple rule-based approach. You can still do it with rule-based approaches, provided you know that you know that the label is on one line and on the next line, or maybe always on 2 lines below. But you have to know exactly how many lines below the label you will find the value, and then you need to make the assumption that they're aligned, and so the label has the same x coordinate as the value. And then you can go like this. With one regular expression, you find the label date. Then you take the word the word coordinates of date and of the x coordinate basically, and go to the next line and look for whatever text you find, whatever words you find at that coordinate, the same X coordinate. And then to be sure how much you want to extract, you don't want to get this part here, the 1, 2, 3, 4, 5, just the date. You need to apply a second regular expression to constrain the values that you really extract here. Again, small language models and large language models can do this fairly easily. With LSTMs, it's a bit more challenging, but we would recommend these approaches here in this scenario. And then to go even further, we already with vertical aligned label value pairs, you already have a scenario where there's dependencies across lines. If you have a table and want to extract information from tables, that's really a whole different level. So imagine you want to extract this number 250, then you can only interpret it relative to the title of the column. And then you also want to interpret it together with the rest of this row. And what's even worse, the row consists of 3 or 4 lines really, but this stuff belongs together. So this is really challenging. There are some long distance dependencies between this value and the title. You don't know how many lines below the title the value occurs. So rule-based approaches here really struggle, but it can be done, and I will indicate how it can be done. But it only makes sense if you really know the structure of the table very well. So basically, what the recommendation here would be, you cannot do this with just raw text. You really need layout information to understand where everything goes. As a small contradiction here, LLMs actually are pretty good even without the X and Y coordinates here, but I wouldn't count on it. It's not fully reliable if you do that without the X and Y coordinates, if you just throw in the text. But because they understand basically the titles here of the columns, and they understand when a new number begins, even without knowing the X coordinates, they are pretty good at this, but I wouldn't recommend doing it productively. So basically you can do it with a rule-based approach. You can do it with a hybrid approach, more on that in a moment, where you combine rule-based and maybe statistical machine learning. Small language models might already struggle depending on the type of table. And yeah, as I said, large language models can do this fairly well. And they can even, you can even ask large language models questions about the table that you provide as context, and then you can get tabular answers as well, but in a structured way that you can then reuse. So basically, now the recommended approach would be a large language model, but if you don't want to throw a large language model at the table, then you can still do it, as I said, with a hybrid approach of rule-based and maybe machine learning methods. And to do that, you basically have to cut the whole task into 4 smaller tasks, 4 small steps. The first one would be to first detect in your document, which maybe is a PDF, detect the area where the table is located. This can be done rule-based, but also with a trained system. I won't get into the details of that. And then once you have the table area, you can look to find the boundaries of between the columns. This can also be done again in a rule-based fashion. If you know the table structure very well, you can just define the coordinates of the columns, or you can say I let them start basically where the labels start, but that's very unreliable. But you could also cluster the content that's indented, that has the same X coordinates. You see here that this stuff is nicely aligned. There might even be some lines that help you that you could use. So there's all kinds of things you could do here. Then the next step would be to detect the logical rows, which can contain multiple physical lines, right? And you could basically say in a rule-based fashion, a new row starts where there's a number here in the line column, something like that, or where there's a value in the reference column. And so after these 3 steps, you have kind of a grid from which you can detect the content of every single table cell. And with that, you can then interpret both the titles of the columns, but also the contents of each cell. And then you can go one step further. In some cases, you detect, maybe you extract the full cell content, like in these cases here, but here in the description column, it's more complicated. There's more multiple values in the same cell. So then we are back at the scenario where we have horizontal label value pairs, like custom code that can be the label for this value here. Or you basically take the first line inside this cell, and that's also a rule-based approach to extract this line here. So that's the way to cut it down into smaller problems if you cannot use a large language model to process these table structures. And yeah, depending on the table structure, you can also train a system directly, of course, without rule-based stuff, but normally the best approach is to do something that takes into account anything you know about the table structure and then really put that into your algorithm because the quality that you achieve is much, much better, even though it's more work to do that for every single task, again, from scratch. Yeah, and then conclusions for information extraction. Basically, everything that Olmo said for text classification also applies for information extraction. But in addition, there's some more takeaways. First, the recommended approach that you use depends really on how the information that you want to extract is used in the texts. Is it running text? Is it more like label value pairs? Is it tables? And there are other things that look a little bit like table-like structures, maybe enumerations with a kind of a little heading or something like that. If you have to do table extraction, again, as I just said, LLMs might be a good choice, but if that's not an option or not good enough for the specific type of table you're looking at, then a hybrid approach with those 4 steps is recommended. But never try to use this 4-step approach to build a solution that should work for all table types. That's not going to work. So as I said before, limit the solution to just the table types that you care about, that are relevant for your task, and then use all the constraints that you know about these tables in your algorithm. And that's already the end of our presentation. And we have a couple of minutes left for questions. You can ask them if you unmute yourself, or you can just write your questions to the chat. I think there already is one. That's just someone leaving. So any questions, please let us know. We're happy to answer them.
Yeah, thanks for your nice talk. Really interesting. Maybe I can go first. So in your talk, what I took away was this dichotomy between rule-based approaches and LLMs. On the other hand, are you at Karakun also experimenting with approaches that combine the best of both worlds? For example, having an LLM develop a rule-based algorithm?
Yes, good question. I think Olmo briefly mentioned one case where he actually created regular expressions using an LLM. So the ultimate goal was to build a rule-based solution because the problem in itself was kind of rule-based, and it makes sense to do that. But the LLM helps to build these regular expressions. They can become very complicated. So that's one way of combining things. Also, when it comes to table extraction, you can easily see how an LLM can solve much of the task, but there maybe is some task left. I can maybe go back to this one slide here. In step 4, the LLM could come up with these cell values, but then maybe you know exactly how the data format of these custom codes look like, and a regular expression would be much more reliable to find this number 340421 even without a label, because you know the inner syntax of this type of data. The same is true for bank account numbers, IBAN numbers, right? There's an inner syntax, and it's fairly easy to build a regular expression for at least if you know the country of the bank account, to find that inside text. So there's all kinds of scenarios depending on the task where they can work hand in hand, and you have to split down your overall task into smaller bits, smaller pieces, smaller subtasks. And for each subtask, you have to decide from scratch, independently, basically, which solution works the best here. And as Olmo also emphasized in his part, it's I would, for each task, always start out by challenging if an LLM is really needed, because they are expensive, and sometimes really cheaper approaches are just equally good, or maybe even better. If you know the problem and that the problem is rule-based by itself, then why use something that doesn't know the rules, right? I hope that answers your question, Yannis.
Yeah, thank you.
There's a question coming in. Do measures like TF-IDF still play a role in today's text classification solutions? Olmo, do you want to take that? Otherwise, I can say something. So for search systems, for information retrieval, TF-IDF, of course, still plays a role for sorting the results, the documents that you find, and so there's still a place for that. But for text classification itself, I would say that unless for very specific types of classification tasks, it's probably not really state of the art in my experience. Thanks. So, any other questions?
If not, then I want to thank Holger and Olmo for your detailed and very informative talk. Thank you very much for taking the time.
Thanks a lot,
Thanks.
Johannes. Also, thanks to everybody for attending. And
I just have one question.
Sure.
In case where it's not possible to use LLM because they are costly, how the OCR errors or speech-to-text errors affect the performance of the document processing? Because the other approaches require the text as input, not the image or speech.
Yeah, that's a very good question. So basically, if we have a scan and we do OCR and then have this raw text, and if the results of OCR are very bad, like maybe it's an old document where the page is already kind of yellow and the font wasn't very easy to read anyway, even when it was a new piece of paper, or maybe just the scanner was not that good, then you will sometimes have just gibberish in your resulting raw text. And of course, from gibberish, you cannot, if the information you want to extract is really badly extracted by OCR, then it's very hard to do something about it. But if it's just maybe one letter in the area that's of interest for your information extraction task, then there are ways to make this more robust. There are ways to include a dictionary and a list of maybe names that can occur in these documents, and then kind of have at the word level some correction mechanism that could be happening in here, or in this arrow from the raw text to the clean raw text, where you correct for OCR errors. Many scanners or OCR tools actually already do that as part of the OCR process. You can configure them to kind of prefer existing words over non-words if an extracted or a digitized word looks almost like a real word, but there's one character maybe wrong or missing. So that helps to clean that up. But also during the text processing step later, you can have some kind of fuzziness in the process, so it reacts more flexibly if something looks like something you want to extract, but you don't recognize it directly. And in the worst case, if you do person name extraction, then in the worst case, you extract it with just the wrong spelling, right? Then it's not Peter, but maybe the T replaced by an I or something like that. So the result could be wrong too. But this is only when there's just a few characters badly extracted. When you really have whole chunks of text where nothing is really correct, then you have no chance to fix that.
Thank you very much.
Mm-hmm.
Okay, so with that, I'm going to end the meeting. Thanks and have a nice evening. Bye,
Thanks.
everyone.
You too.
Thanks, everybody. Bye.
Bye-bye.